now unfortunately, we don't have much time for the question answers session. We had planned it 20 minutes, but we're going to reduce it to 10 minutes. So we expect questions from the audience here and also from people that are logging remotely. Camilo?
Well, yeah. Regarding the discretization of the full size in the rupture generator, I always have seen that as a problem of which is the minimum sampling that we are doing in our simulations in the wave number domain to understand then which resolution we need in terms of the subfold dimensions. So, well, you got something like that also, that at the end is inverse to the frequency and also to some reference VS value. But for example, in some cases, depending if we are solving the wave equation in softer materials or in stiffer materials, we will have longer wavelength or smaller. So, which is your thoughts about setting the subfold dimensions in an approach like that? And in general, what do you think? No?
Yes, thank you for the question. So if I understand correctly, what you're thinking about is, well, typically just in terms of wave propagation, we have say a minimum sampling that we need in our grid domain, whether based on the wavelengths. And I think it is similar to that. However, the rupture propagation, even though it may be correlated with the local shear velocity in the model, it's not necessarily true. And so but I think it's a similar type of argument. So we have say a minimum wavelength that we want to resolve, but it's in terms of the rupture propagation, not in terms of the wave propagation in the model. And so even though there may be some correlation there, but that value that I quoted, and it's not a super rigorous, but 200 meters per second, even if the local shear velocity is 3 kilometers per second, you can imagine that the rupture may just go very slowly in that portion. And in order to resolve that, we would need a resolution that is much higher than what we would get just for wave propagation. And hopefully I understood your question correctly. Hopefully that provides some answer.
So Arvin, I have a question on the number of realizations. I can do it now, or I can hold it to the panel discussion.
Because it's going to be part
of the discussion. Okay, fine. I have a question for Roberto, but I'll hold it.
Okay, yes. Any other question from the people that are remotely following us? How can we, I don't
see anything there.
Oh, okay. Do you see any questions? No. Okay, all right. Okay, Ree, go ahead.
I have a question to Martin. So you talk about the important dynamic rupture modeling to constrain the kinematic rupture modeling. So there are a bunch of parameters in the dynamic rupture modeling, like for example, friction properties. You talk about roughness or the fluid flow, pressure. So are they needs to be treated deterministically, or how are we going to I that, or do we? That because that's going to affect the kinematic rupture model, that's going to be the next step. So that's one question. And I do have one more question. So a lot of people talk about asperities, or how are we going to handle asperities? Like, can we handle as a random heterogeneities, or so that you have that, or should we treat them more dynamic, deterministically? If you can, share some thoughts on that, that'd be great.
Okay. So I understood the question was directed to me, and I understood the question had two main parts. The first part was related to how do we constrain the dynamic parameters that go into the dynamic rupture simulations. And if I'm correct, there was a connotation if these dynamic parameters are somehow used also in creating the kinematic rupture model generators. Was that the question? It's very difficult.
So the first question is more like the parameters like you use for the dynamic rupture modeling. So like frictional parameter, frictional properties and the stress conditions. How are we going to constrain that? Because that is going to affect, like if you're going to use that to the kinematic rupture, the model building, that's going to affect the second space. That was the first question.
So let me just make a few comments on this. You're asking actually a very important question. Rob earlier said that kinematic rupture simulations are simpler in some way and computationally simpler, but dynamic rupture simulations are physically more correct. That's true, but in the dynamic simulations there are many parameters that we have to define in advance, and the geometry of the fault and the stress, etc., are just a few of those. I described the work of Art Frankel and also a general understanding that we have now from observations, from theory, etc., that stress on a fault is heterogeneous and it seems to follow a fractal decay. And that's also determined by work of Smith and Heaton and others when you look at very near source moment tensor inversion, stress heterogeneity from those, etc. And so we can constrain the heterogeneity spectrum on a fault, but it's a stochastic one, so it's not a deterministic one. And over this, we have depth-dependent normal stress, and we have a regional stress tensor that acts on the fault. So these three conditions essentially give us a way to constrain the initial stress field on the fault. When you then do the dynamic rupture simulation, you have to make assumptions about the friction model. So, how does the fault break, like the rock on the fault, how does it break and how does it slip from the peak strength to its residual sliding friction? And there are various ways to parameterize that, and each has slightly different effect on the dynamic ruptures. This is constrained from laboratory measurements and from theoretical considerations, but again, it needs to be parameterized. So in essence, when we do the dynamic rupture simulations, we have to make many assumptions. And some of these parameters we extract from the lab, some we can constrain from observations, some we basically have to make up, let me put it this way. But at the end, we constrain the dynamic rupture model so that they reproduce ground shaking, that they reproduce observations of past earthquakes. And so we begin to be quite confident that these simulations are stable, robust, trustworthy. Now, the second question was related to asperity. And I sorry? Oh, okay. Let me see. Because I understood part of it. No, I don't see. Open question. Yeah, please read it to me. I don't see which one it is.
It's regarding where does rupture starts in slide 12 in your presentation. And there are different rupture generators. May I know if the conclusions are similar for what different rupture generators? Yeah, so Martin, you are muted. Oh, sorry, maybe I should mute my...
Maybe
Martin is muted. Martin?
Yes, all rupture generators suffer from the same problem. We have to assume the hypercenter somehow. So you have simulated your slip field on the fault, and then you place a hypercenter. Or the other way around, you say, okay, I want the hypercenter at the bottom of the fault, sort of 2/3 down from the west, just as an example. You place your hypercenter, then you generate your slip distribution, and then from that you do the rest. And so in these cases, the hypercenter position is chosen arbitrarily and is not necessarily compatible with the mechanics of faulting. and the dynamics of how ruptures nucleate and propagate from a stress patch that happens to break. So I'm trying to find out. So that's a problem in general, which we have to resolve. And what we found in this 2005 paper, examining about 80 or so finite fold rupture models that have been obtained from waveform inversions and things like that, is that the hypercenter is located such that there's a spatial correlation with the areas of high slip. And so the hypercenter does not appear somewhere at random on the fault, but instead it is correlated with slip. And the actually to put this in the physical logic is such that once an earthquake nucleates in the fault, it needs to receive an initial, let's say, stress pulse or stress release that feeds energy into the crack tip. And then the rupture can propagate, and then it sees another region, let's say, which is highly stressed, but then the dynamics allow it to rupture through that patch of high stress to create a large slip patch in disparity. And so that's why you have that sort of spatial relation between hypocenter and large slip patches. In principle, it's very difficult, but not impossible, for an earthquake to start at the region of the highest stress on the fault, such that at the end you have the hypocenter at the location of the highest slip patch, the strongest disparity. But this is that's an explanation that for the observations we made. And in my opinion, when we run our rupture model generators, we create an initial slip map on the fault, then we need to use that idea to place hypocenters that are mechanically viable and dynamically constrained, and basically have a condition on where to nucleate the events once we have the slip heterogeneity defined.
Martin. So we'll move on now to the next session, the panel discussion for this session, and I would like to invite the panelists, Rob Graves and Chiara Smerzini, who are present here. But then we have online Brandon Bradley, we have Roberto Paolucci, Riccardo Taborda, Martin Mae, and myself.
Okay. Can we promote them to panelists, Christina?
So can we use this microphone now?
Yeah. So you would pretty much have to moderate it. You will say somebody speak online, and then he will activate them, and you say somebody speak here, and then he will activate them.
Okay.
If he activates both, there will be the feedback.
But then for the audience, we need to use this microphone.
Yeah. Mm-hmm.
When is it on now or not?
It is on now.
Okay, all right. Okay, so we have about 20 minutes. Unfortunately, we kind of running out of time. And so the question that I have included here in this PowerPoint were selected among us as a member of the panels. But of course, the discussions that we may have may not be just focused on these questions. We just wanted to guide you. And if there are people that would like to know about other things that are related to rupture modeling, please feel free to ask to the panelists or even discuss about them. So one of the focus of this discussion will be how realistic and is our variability in our representation of the source rupture. And there are several questions here. One of them is how can we make progress with parameter uncertainty distribution for rupture generators? What sampling criteria should be followed that Rob talked a little bit about and other people? What is the probability that a super shear rupture occurs that we talked a little bit about today? What is the probability that the fault breaks the ground surface and up to which spatial extent with respect to the total fold length. The other question that we will discuss today is the number of rupture realization, although a couple of speakers touched upon a little bit about that. The other topic is multi-segment faults. Those are very important. How to tackle multi-segment ruptures in kinematic rupture generators with appropriate dynamic constraints. So the dynamic rupture generators for multi-segment ruptures, including rupture jumps. And rupture nucleation, that was also a theme of discussion that we had today. Where does a rupture start? Can we develop a physical constraint useful for kinematic rupture generators? So I will start with the first question that is related to the uncertainty distribution for rupture generators. Maybe Roberto or Ricardo would like to talk about this.
Okay, I may just say that again from say an end user perspective, since I'm not say an expert, of course, of source characterization. We actually faced the implementation of different source rupture model generators, and we faced typically the problem of say somehow governing. Okay. I hear a echo in my voice. The uncertainty in the parametric distribution, especially those that Martin was mentioning, the one of say addressing the hypocenter location, again if considering a super shear. On one side, we need some input on from that point of view, from an input from a seismologist. That is, as I have shown in my presentation, it really matters the possibility to better tune the range of possible ground motion and the probability distribution. So if these, of course, for example, in our simulations, we fix the super shear, we fix the rupture velocity lower than shear wave velocity in order to avoid super shear ruptures. But still, it is something that we have fixed in this case to avoid the very large values, but we are not really in the position of governing these parameters. So really having some input on that side would be really beneficial. So I do not have a specific, say, well-defined answer to that.
Yes, good morning to everybody. Just following the comments made by Roberto, I would like to add a similar remark. Of course, I'm not an expert as well in rupture modeling, in kinematic and dynamic rupture simulation, in modeling and parameterization, but I can bring here some remarks on end user, on a user perspective for engineering application, as Roberto said a few minutes ago. So what we found is when using the kinematic rupture modeling, because the dynamic rupture simulation are too expensive for engineering application. Expensive because they are computationally demanding, expensive because the definition of the input parameters require special attention. But also in a more simplified source modeling like the kinematic modeling, the parameters that are used as input are many, And the correlation, the temporal correlation, as also Martin Mein stressed very well before, the correlation between all the kinematic rupture parameters may be tuned very carefully, because it's especially a correlation that is not physically based, that is unphysical from a seismological point of view, then lead to a variability in the ground motion that is not realistic. And so, especially is in the correlation between the kinematic parameters that is not well set from a physical point of view, then the shortcoming from the ground motion distribution is that, especially in the upper bounds that are not realistic, or in the variability of the ground motion that we can observe and that matter for the engineering application. Also for the super shear, we tend, as Martin Mein stressed before, yes, that's true, we tend to avoid super shear, like a nightmare for us, because super shear, especially if combined in kinematic rupture model that are rather simplified, planar source, homogeneous near surface geology, then tend to give a behavior in the ground motion with unrealistically large amplitude values that are not observed, unrealistic, because they are not observed from ground motion records. So yes, so this is just I wanted to do this additional remark. Thanks.
Yeah, just to add my couple thoughts on this, I would draw the analogy to, with developing ground motion models. We use ground motion prediction equations, and David showed the plot of the distribution of, magnitude versus distance in the NGA program, and there's holes there. Well, the same thing is true from a seismological perspective in trying to develop these models. We have slip inversions. Those are not direct observations. Those are inferred models. Right? So there's uncertainty there in terms of what is the slip distribution? How fast does the rupture propagate? We have, there are cases, some cases, limited cases with super shear rupture. How often does it occur? Does it occur across the entire fault or just a portion of the fault? Those are very important questions. And yes, it can be incorporated in the models, but we just don't know how often or what the parameter, the probability distribution of that is. And so I think it's a very complicated problem, and again, we're faced with kind of this issue of limited observations. I will say, one of the ways around that, and I think most, if not all, of the kinematic or rupture generators use some level of correlation among the parameters. So for example, if you specify the slip distribution, that gives you some idea of what the rupture speed's going to look like, or what the rise time's going to look like, or, as Martin had just talked about, where the hypocenter should go. And there's always this process of making sure that there's this continual feedback with validation and also checking with the dynamic ruptures. So, it's a complicated problem. Unfortunately, we don't have a simple answer, but it's something that will evolve and I think improve with time.
By the way, I put up a slide that you prepared. So if you want to touch a little bit about what you want to say about this sampling in kinematic parameters.
Maybe I can use this microphone.
Yes.
Yeah, so I'll go through this quickly. I mean, a lot of this is kind of, already been talked about, the different parameters we might consider. I did put one here, creeping zones. We're talking about the Hayward Fault. Calaveras is another fault where, there's creep observed at the surface. It's aseismic deformation. And that adds yet another element of uncertainty, right? How do we parameterize this? I'm actually showing these slip plots, two different ways. The top plot is no creep, and then the second plot, I've just tapered the slip in the near surface to, kind of mimic that. We don't really know what's going to happen when a rupture propagates into these creeping zones. Will it just propagate through like a normal rupture? Will it, the slip be decreased in some way, or, how will that happen? So again, lack of observation. We can explore that with some parametric studies. But again, just to reiterate, I think that for particular faults, this may be an issue. And then the bottom point here, the kind of the number of samples or what we might sample, I think is problem dependent. We need this feedback. And it could even go all the way, from an engineering perspective, what types of structures are you looking at, where are they located relative to the fault, and so forth. I don't think there's a single answer again, but I think it's this communication that would be important to develop those rules.
Can I ask a follow-up on that real quick? I mean, there's a lack of data certainly, but we know what's in our computational models. So we can explore this sensitivity numerically and not wait 20 years for the next data set to come along, I would presume. And I'm just curious, and maybe Chiara and Roberto can chime in on this, they came up with a conclusion of 10 realizations of that order. We've been approaching this in an entirely different way that you just alluded to. We've been looking at trying to settle down the statistics of the demand on the structure versus the number of realizations. Remarkably, perhaps, and it's still pretty ad hoc, we're coming out with a very similar number. We had 10 to 12 realizations for a magnitude 7 earthquake. I'm just wondering if anybody has developed the intuition based on simulation yet of the sensitivity to various parameters, or has it just sort of been randomly turning the knobs, or are you beginning to solidify a notion of what parameters we need to vary and how much to settle down those statistics?
Well, I'll comment kind of quickly, but I certainly would like to hear the other panelists' perspective, because I think there may be some differing points of view. I'm a little concerned when we derive these types of numbers, and I've kind of gotten to that same point, maybe 20-ish or so realizations. And my concern is that we tend to look at that with a single kind of rupture generator. And I think we need to consider a broader spectrum, just as traditionally has been done with ground motion models, right? You don't just use a single author, you use 4 or 6 or whatever. So I think we need to start testing that, as you said, David, from a kind of a parametric sense, just see what happens. If we use different rupture generators, does that increase the number that we might have to consider? And there are, different classes. I think, for example, the Japanese Irakura method is quite a different approach. So I think we need to start looking at that. And as you said, now with the computational expertise or capabilities, maybe we can just explore the parameter space. So others, please comment.
So we have Martin first and then Chiara second. Go ahead, Martin.
I want to make one quick comment on the last question. I was actually very surprised to see or hear that only 10 to 15 simulations should be sufficient to capture the uncertainty. From a purely statistical point, that wouldn't make any sense, because you need at least 30 to 40 samples to constrain a normal distribution well. I mean, that's taught like in Statistics 101. So I don't see how 10 to 15 simulations can be sufficient. And I would then ask the question, what do we mean by realization? Realization of what? Let's say you have assumed a fault plane and you fix a hypercenter and then you make 10 realizations of the slip and the temporal rupture. Or do you say, I'm actually approaching it from a point of view that my fault can be slightly differently oriented within a given volume. I don't know the hypercenter, so I have to randomize over the hypercenter, I have to randomize over the slip distribution, I have to randomize over the correlation length of the slip distribution, etc. So I don't know what 15 realizations means. And my impression is intuitively that this number 10 to 12 to 15 is an, let me say, artificially low number, but just the way of how these models were constructed and how they were tested. And so I agree with Rob, we need to do this with multiple rupture generators and then be really clear about what do we vary and what does one realization mean in this vast parameter space. And the other comment that I would like to make is a bit broader. I try to mention that the rupture generators we've created now, and the Japanese and the Archuleta and so on, they are built on a fairly small number of dynamic rupture simulations under very confined conditions, limiting conditions. And secondly, let me say, research team A has its dynamic rupture simulator and has created 50 models and does an analysis. Research team B does the same with 20, and research team C with 100. But we don't share that information. And so let's say my dynamic rupture models, they sit on my computer somewhere, and nobody else uses them in a different way of analysis, let's say. And in my opinion, what really should happen is that we build similar to, a database of ground motions and a database of finite fault rupture models, etc., that we build a repository of such dynamic rupture models in some unified format, and then anyone can use this information and actually has access to hundreds, or even thousands of dynamic rupture models in order to build more comprehensive and better informed rupture model generator. And to kind of augment that point is what we haven't done from a dynamic rupture community is to really try to scan the parameter space and stress heterogeneity, different friction laws, different magnitudes, etc., for the sole purpose to create a rupture generator. So we're interested in a dynamic rupture community to study a specific earthquake, like the Turkey earthquake I showed earlier today. How did that happen? Or we try to understand, the interaction of 2 or 3 faults, etc. But we haven't made the effort to have targeted dynamic rupture simulation for the only purpose to inform, rupture generators for the future. So that could be yet a different strand of activity where we engage and share these models and build a database of dynamic rupture models as a product for future use.
All right, thank you, Martin. Chiara, before going to you, I would like to read a couple of comments that we have from the online audience. And then, yeah. So Ruth Harris has something related to what Martin said about the stress heterogeneity on the fault. So she said that I agree with Martin about stress heterogeneity. For dynamic rupture simulations, we need to know the fault geometry, the friction behavior, stress conditions, and rock properties. The fault geometry and rock properties are the same as what we need for kinematic rupture simulations. The fault friction and the stress are unique to dynamic rupture simulations. These are tough ones to figure out, but we have made some progress, as Martin has described. And I agree with Ruth. We have done some progress with that, and certainly we look after the dynamic rupture modeling groups to give us some strong constraints on the kinematic rupture models. There is another, Ruth made a comment, Rob, hi Rob, we have been simulating large earthquakes on the creeping Hayward Ford and Calaveras and Rogers Creek faults using dynamic rupture simulation. So this is, so Harris and et al. In 2021. So yeah, this is something very interesting, at least for the work that we're currently doing in the Bay Area. And then there is Brad Eggert, who has a general question here, and I'm hoping somebody will answer this. How do we ensure that we capture the full epistemic uncertainty for rupture generators? We have no more time to answer this question, but if somebody wants to, so we didn't hear much from Brandon and Ricardo. I apologize for that. They really asked some really good questions, but the time is so limited. So if you guys want to say something to this audience, this is your chance for today. But we have several.
For the topic. Right?
Yeah, for the topic.
Okay, Alvin, can you hear me okay? Arbin, can you hear me okay? Okay, Ricardo's saying you can hear me, so I'll talk through the echo and hope you guys can solve it at your end in parallel. I agree with Martin about the sentiment around the number of realizations. That clearly it depends on what you define as the scenario, whether you're already talking about a fixed geometry, a fixed hypercenter, and you're just varying the slip, or whether you're talking about randomizing those parameters. Or from a statistical perspective, I think we can just think of it as how many samples do you need to adequately represent the distribution, and numbers on the order of 30 plus seem appropriate. But it also comes back to what measure of the ground motion distribution you're actually talking about. If we're simply talking about the mean ground motion intensity response vector for some period, then maybe the total number of realizations can be less than if we're thinking about how does that ground motion then affect some particular building, some peak displacement or peak moment in some location in the building, where coming back to things like what Roberta and Chiara are mentioning, super shear or not, may have some sort of bimodal effect on the demands on the building, and therefore the likelihood of those is going to strongly influence things. So I would say broadly, Rob's general sentiment of sort of it depends and it needs to be problem specific is a good guiding principle, but it's likely that with some level of accuracy it's going to be 30 plus realizations rather than sort of 10, albeit that may illustrate the level of precision that engineers actually care about, that if we're just talking about estimating the mean ground motion intensity plus or minus 50%, then probably 10 is enough. The other thing, the first comment that was mentioned about parametric uncertainties, I think is really important, because Roberto alluded to how 3D simulations can be used in probabilistic seismic hazard analysis. Obviously, there are many applications for 3D simulations, but the holy grail would be where we can estimate the distribution of ground motion, both mean, standard deviation, and range with good accuracy. And so that clearly requires us to define the uncertainty distribution adequately. I think that's also the general answer to Brad's comment, or the general question that Brad was framing about that epistemic distribution. And really, in my opinion, the only way to get a handle on whether we're constraining that adequately is through validation against observed ground motions. And so I think the challenge there is that, as Rob alluded to, when we look at slip inversions, they're not actual data, they're a model inference of the data. And so really we can only do that by comparing simulated ruptures and the resulting ground motions at locations of observation. And naturally, as we go to the frequencies that we care about for engineering applications, that means that really we're not just measuring the quality of the rupture generator, we're actually talking about the 3D earth structure and the very near surface site response as well. And so we have to untangle what is the role of source in those observed ground motions and try and tweak our rupture generators to be consistent with the observations. So those would be my general comments. Thanks, Alvin.
Thank you, Brandon. Well, unfortunately, we are running out of time. I would like to thank again the speakers and the panelists for very interesting presentations and discussions. Certainly, these are really important questions that we would like to continue discussing through probably other workshops and maybe some other papers. But I think we should keep up with the discussion and the interaction among the practitioners and the scientists that are focused on both rupture modeling and earthquake ground motion. So again, thank you very much, and then we'll move on to the next session.
Yeah,
we have a break. Okay. Thank you.